it's not really a camera. It's all the activity that happens on the smartboard with my voice. That's so if you go to one of those videos, you'll see this screen and my voice, and then the guy just never shuts up. Just keeps talking just forever. Okay. So we're going to talk about limits. All right. A limit. I think we started talking about limits briefly the other day, right? Yes, some other things that probably scared some people. Now, okay. A limit, first of all, notation. Usually it's x, although it can be any variable. Okay, so this is saying the limit of a function as a variable approaches some constant. Okay, so what this is saying is some function of x is changes as x a and the f direction. Okay, so for example, we've talked about the idea of like an edge crawling on a surface, or creeping up to something. That's the idea. So we have some constant a location of an independent variable that we're walking towards, and we have and what's going on is that you're moving along the surface from both directions towards that thing, whatever that value is. Now, very often you will find that the point on the curve that you're approaching might not even exist. It might be surgically removed, like a hole in a function that we dealt with. When you were factored living daylights out of everything, you set your cancel terms to 0 to find the holes. That might be a hole. Okay, it might also be an asymptote. Okay, and we'll be playing with all things. So, just for the record, there are two other limits that you can not just be approaching it from both directions. You could be approaching it only from one side or the other. And those are your left hand and right hand limits. Yes. This is very, very similar. As x approaches a from the right. Okay, so in fact, it says the plus sign is almost kind of misleading. It's not like you're heading towards the positives. You're not moving from left to right. You're actually moving from the right towards the point in question. Okay? So this is what is called a this is a right-hand limit. Where you're coming from the right. Okay? And obviously the minus sign is the left-hand limit. All right. They don't have to be the same. Okay? For example, I'll make sure everyone copies this. All right. Here's a simple case where not the left-hand side and the right-hand side are not the same. So do it. All right. So if I have a function that does this, this guy from the left-hand side heading towards 5, whatever, okay, if approaching 5 from the left, it would be a different value than if I was approaching 5 from the right. Does that make sense? So let's call this 7 and 3. Okay? And in fact, actually, if you don't mind, I'm going to modify this just a tiny little bit and play with it even more. Let's call that 6 and 5. If I approach 5 from the left, the value would be 7. So limit as x approaches 5 of f of x, whatever f of x is, some goofy thing. This equals 7. Limit as x approaches 5, sorry, from the left, from the right. This guy equals 3. And the function itself doesn't even equal 7 or 3. It equals 5. Okay? So now, things don't have to play nuts. And now, the problem, well, not a problem, but the thing that is that what if I was approaching different directions at the same time? If I was taking the true limit as x just approaches 5, f of x, does this, what is this? What do you think that is? It's kind of like, if you had a GPS and you and a buddy both had a GPS and you were in Arizona or Colorado and you said, hey, we're going to go geotracking and, you need to find yourself at this latitude and longitude. All right, so one of you comes in from California, one of you comes in from Virginia, and you both come to the same location, and it's the edge of a cliff. You're on top of the cliff, they're at the bottom of the cliff. Are you in the same location?
From a top view.
From a top view, sure, but are you really in the same location? No, not really, because you can't shake hands, right? It's undefined. Does not exist. In order for a limit to exist, it must be the same from both directions. Okay? Now, this idea that you could approach it and you would both be coming to the same location. Yes. Because we told it to be. We said it was. For example, I could create this thing to be that if I wanted to, but like as a piecewise function, or like let's just say maybe this was some sort of definition of a median, in a sense, where I have one side of values is all like if I created a list of values, really, really big positives and really, really big negatives. And as I approached the center, I would have an even number of terms and I'd have to take the average. That point didn't exist in the set, but I can insert it and say, this is the median. Does that make sense? Or even still, I could make a piecewise function that would do that. And I could say, if you were standing at 5, you're living at 5, 5. Okay? Different ways of playing with piecewise functions is fun. But in fact, there's a 3-part definition to this, to this concept that you see this line is broken, right? In order to draw it, you must take your pencil off the paper, which and mathematicians are very creative in their language, and they call this a discontinuous system. Okay, this is not continuous. And continuity is an important topic, and we're going to talk about that right now. Continuity. If something is continuous over an interval, then that means when you draw it, the paper, your pencil never comes off the page. That's like the layman's definition of it. The Feynman definition is you never take your pencil off the paper. Now, that's not really a mathematical definition of something, especially if you have a graph that you don't know how it graphs. You know, you don't have a function you don't know how it actually graphs itself. But in fact, there's a three-part definition, a mathematical definition to it. And in order for something to be continuous, it must behave in the following way. The left-hand limit has to be equal to the right-hand limit. Okay? Just like the picture before, that picture failed for that reason right there. Okay? So right off the bat, if it's broken in that sense, no dice. The function, the point has to actually exist. Okay? Okay? But it can't be a whole, right? Because if you think about the idea behind a whole, that if I was drawing my pencil on that paper, just like I did just there, I had to take the pencil off the paper because a point is missing. Okay? So therefore, that curve that I just drew, that sketch, is discontinuous. And third, that the limit, the pure-handed, the honest-to-God limit, the double-handed one, has to eat function itself. Something like this fails. Where this guy just doesn't play nice. You know, I have a point, I've surgically extracted it and inserted it at a different value. Okay? So if you were to think about this for a minute, an example of this happening, x to the 0th. Think about that function, x to the 0th. As x approaches 0, if you look at this graph, anything to the 0th is what? 1. What happens at 0? 0 to the 0th is undefined. It's a missing hole. It's a spot taken out of the picture. Okay, anything, because if you think about it, if you have 0 and you have, okay, think about an integer, any integer, 1, 2, 3, 4, 5. As that thing, if I write that number down no times, if I write, for example, that, this is saying that I have a shopping list and I don't write tomatoes on it. I write beef once, fish once, corn once, and I don't write any tomatoes. Does that mean I don't have a list? No, it just means that that item is not written down. So in a sense, you could say that it doesn't have any effect on my list. That term is called nilpotent, by the way. Having no effect. Yes. Yes. If someone is nilpotent, then they are totally useless. They may not be useless, but they certainly don't change anything. Wait, yes, the academic way of insulting people. Wonderful. let's move beyond this, but we can that point has been removed from my term. So I have three different kinds of limits. Three-part definition of a limit. All right. So let's have some examples. All right. I have a good couple of ones picked up here. Yeah, let's do some of these. All right. Now, sometimes evaluating a limit is just as simple as plugging the thing in, especially if you know that the function is continuous. So, for example, limit as x approaches 2 of x squared. What does this function approach when it gets, well, first of all, can I plug in 2? Yes, and that's almost always the first step, is to just see, hey, does the function exist? Okay, and if it does, that's great. If it doesn't, then, we have to play with this. This is equal to 4. Wonderful. But now, if I plug in 0, what happens? 0 over 0. 0 divided by 0 is a problem. And this guy fails. So if I were to graph this function, it would not exist at 0. Okay. But what can I do to this? How can I make my life a little easier? It's not irrational. Yes, you can factor the invariance out of this. And by the way, here's a great way to lose points when somebody really super critical is grading your paper. Now, I make this mistake a lot, and I have to be careful about it. But I bet you that if you were to paper on an exam, like an IB exam you had to submit to some other foreign country, if you didn't write this before your next step, they would probably take off points for that, because what you're saying here, if you dropped this for a second, just for a minute, and just wrote that, you see, that's not really true, because this is a function, right? And when you take the limit, you get a number. Yeah, that's a problem. So don't forget, if you're playing with your limit, to keep that notation out in front until you actually perform the limit. Okay? So I just don't want people losing points over a mistake. But I'm guilty of this. It's something that I often mess up. And I have to say, oh, all right, go back and fix it. Okay? It's easy to forget. All right. So now we cancel. I have to say x not equal to 0 at point. All right? Because now if we go ahead and cancel these things out, we have to leave that in. And now what can we say this is equal to? Now, when you graph this thing, the picture of it is that with a hole missing. That's a bad picture of a hole, but actually. What the picture would actually look like. Okay? And of course you wouldn't see it because it's just a missing point which has no width. Yeah, it wouldn't show up on a pixelated picture. All right, are we cool? So my advice is, when you're asked to take a limit, first, just go ahead and try it. See if it flies. If it doesn't fly, if it does fly, great, you're done. If it doesn't fly, then factor the living daylights out of it. See if you can get it into some sort of form. Maybe you have to modify, twist, and bend this thing in order to get that problem, and in this case, the problem was division by 0, out of the picture, okay? All right, so let's try this one. All right. Do I have any better ones first? All right, let's try this. No, that's an ugly looking infinity. Still an ugly infinity. I'm all right with it though. Of x squared minus 3x plus 2 all over 1 minus x squared. So, like I said, first thing you want to do is plug it right on in there and see what you wind up getting. And what do you do? What happens when you plug in infinity into this? What happens? It's a what? Well, if you plug in infinity, you get infinity squared, which is what? Infinity times infinity is, it's infinity. So you wind up getting infinity and 1 minus infinity, negative infinity, and this is one of the indeterminate forms. Okay, there are several indeterminate forms. For example, 0 over 0, division, well, this is 1. Another, infinity over infinity, 0 over 0, infinity over 0. What about this guy? Is that indeterminate? That's 0. Say that again?
2 middle ones.
There's only 3. How do you have 2 now?
No, sorry, that,
okay.
We're in the middle.
Oh, that were. Okay, so those are indeterminate forms. Those are no good. And actually, I believe infinity minus infinity is another one too. Because which infinity is bigger? Right. And if you guys are interested in infinity, look up the term cardinal numbers, because they talk about different size infinities. Some infinities are bigger than others. What? Yeah, like think about it. Which are there more of? Integers or rational functions? Rational numbers. Think about that. Or whole numbers. Like for example, there are an infinite number of positive integers, right? Yeah. 1, 2, 3, 4, forever and ever and ever. Your natural numbers, right? But the integers, which are the positives and the negatives, well, the natural numbers didn't have the negatives in them, right? So you would imagine that the natural numbers are smaller than the integers, because there's more integers than the natural numbers, right? But they're both infinite. So we're talking about sizes of infinities. So if you're interested in this kind of thing, look up cardinal numbers. They're kind of cool. So this becomes a problem. So what the heck am I going to do? How could I perhaps futz with this somehow?
Like x squared, so 1 minus x squared equals 1 plus x, and then 1 minus x.
Yes. Factor the living daylights out of everything. It's a good first step. So back to the top, back to the bottom, see what you can do. Can you play with it? There's definitely some funky business going on in here because well you can there's issues here, right? So can we factor the top? And this becomes x minus 2, x minus 1. Now the bottom, you're right, is 1 minus x and 1 plus x, but I have x minus 1, and you know, I'm not so super thrilled with 1 minus. So one thing, and this is just a nice little thing that you should know how to do. If you have a minus b, and what you really want is b minus a, okay, factor out a negative 1. Okay. So now here I can split this guy up nicely and cancel. But I wind up with another problem, don't I? And those guys cancel, and I have to say x is not equal to 1. And now I have x minus 2 over 1 negative x minus 1, right, or something like that. But the problem is, again, when I plug in my limit, I'm going to run into my interpreted frame again. See, if I plug in infinity at this point, I'm still running into infinity over infinity. And I'm not a happy camper. Right? Still no good. So now we have to say to ourselves, is there another tool in my toolbox? Okay, now, for example, let's do this. For a moment, step out of your brain and say, what happens to this function when x goes to infinity? If I make x bigger, what happens to that value? Yeah, it gets smaller and smaller and smaller and goes to 0, right? 0 is a nice number because it goes away. Right? So I could maybe turn some of these x's into something over x, then my limits would vanish. You know, these things would go away. So instead, let's try this approach. This is a very useful approach. X squared minus 3x plus 2 all over 1 minus x squared, right? From the page before? I think I got it. So what I'm going to do is I'm going to do something really cool. I'm going to divide. Well, how about this? I'm going to multiply by 1. Squared is my biggest power. This is neat. This is cool because what this does is it turns all of my exponents from numerators into denominators without changing the value. Watch. and this becomes 1 minus see? Ta-da! And now what happens when I take my limit? What happens to all of those denominators? With all those infinities and all of those denominators, what happens to all the 3 of those terms? Well, plug an infinity into every x. At the 3 over infinity is 0. 2 over infinity squared is 1 over infinity squared is 0. So now what do I have left? What happens? Becomes just 1 over -1 or -1. You see, so that is a tool you need to put in your toolbox. It's really kind of neat because it doesn't change the value of anything. It just rearranges it in a weird, goofy way, and then the limits disappear. Cool? Are we good? Yes? You see how it works? If infinity is in your denominator, you're making your denominator huge. And as your denominator gets huge, the value of it goes down to nothing. It shrinks to 0. That's why it holds. Okay? And remember, this, wait, I'll go back. This is 0. So that's a good thing. Okay? That's the whole trick. Let's try. Oh, of course. Please. Who said that? Okay. All right. Here. Another simple example of that. How would you use that same tool here? Over 1 over x, right, exactly. Because you got to multiply by 1 now. Right. You got it? Okay. And what do we get? Not so bad. Like how? Where?
Like, should I write this next to the 2?
No, because at actually you missed one here. Because what this you can think of as an operation. Okay, it's a verb in a sense, and until you execute it, it's kind of like you're holding it on pause while you manipulate your function around, and then when you're ready, you activate the limit, and then you produce the number at the end. So it should be there until you actually plug in infinity. Until you plug in infinity, it should be there. And the second you plug in infinity, you've taken the limit, and the result is a number. Or it does not exist. Yeah, the end. Okay. Are we feeling good about this? Okay, are we getting better at feeling about this? I didn't have to. All right, try this. Oh, don't you dare. Don't you dare. He said something I didn't want to hear him say. So first things first, plug it in. Plug it in first and see if it plays nice. How's all this looking? Okay, it runs into a problem if you just plug in 3 right now, right? Right. Yeah, that's, I mean, you could plug it in up top, and if you got 0, fine and dandy, but that doesn't mean that it exists. If it falls in the denominator, then you know that it doesn't exist. So, save yourself the energy and do the denominator first, because that's where the failure occurs when you divide by 0. So what are we going to do first? Factor the derivative out of it. Absolutely. Oh, no. Let me ask you this. I thought cancel out the x squareds because of this. This is $1.25, right? $1.25. 5 quarters, right? I haven't broken any rules. Can I cancel? Right. Same thing applies. But I have to think about it in terms of order of operations. The order of operations says, what am I doing overall? First thing I'm really doing is I'm doing a division. Well, I'm dividing 2 things. And the 2 things that I'm dividing have addition in them. It's a common thing. I see it all the time. This. Thank you. Need this. Really need it. Is it available for other Wait. He's in. Oh, there was a stack of those. There were some more. So you factor the difference in. There is a random kit. X minus what? Huh. Yeah, there's a problem here. Why does this not work? Where's the thing that's going silly on this? Well, not only can I not cancel them out, I'm not getting the right thing. Take a look. What are the factors of 6? 1 and 6, right? And 2 and 3. The denominator. Yes. Right, I know. Look, that plus tells me that these 2 things have the same sign, so this doesn't fly. Instead, what I have in there is x minus 3 in my first block. Take that. Now it plays I'm sorry. Yeah, I'm sorry. It happens. And you see, I haven't yet pulled the trigger on my limit, and now I do. And I get 5 all over -1, so not -1, damage, which is fine. Okay, so factoring is a great point. Wait, I had another one. I'm sorry. Go ahead. All right. By the way, a piece of vocabulary that I often use is this. This is what is called a monic polynomial. Monic, mono meaning one. It has a leading coefficient of 1, okay, where it's 1x squared versus, say, 5x squared. You see those polynomials as well, right? Like this. Where the top is a non-monic, whereas this is a monic. Just so that you know that vocabulary. Now, a lot of people have a lot of trouble factoring non-monics. Yes. Yes. Okay. A non-monic polynomial is a pain because we don't have that 3 in front and we can't just break it up right away, right? Some people even go so far as to say like yes and check, or plug in random numbers and hope that one of them actually works, or something like that. All right. In fact, here, has anyone seen a guy pull a rabbit out of a hat? It's one of my favorite lectures. Even if you've never seen a guy pull a rabbit out of a hat, you're familiar with the magic trick. Okay. Well, that guy, before he pulls that rabbit out of the hat, listen. Yeah, well, listen. Before that guy comes out on the stage and pulls that rabbit out of the hat, that backstage, he stuffed that poor little guy in there. Right. And, he's got other tricks besides pulling the rabbit out of the hat. He's got to put flowers in it someplace. He's got to cut some poor lady in half, make something disappear, all that stuff, right? So if he forgot to pull the rabbit out of the hat, and he went home for the weekend, and that poor little rabbit was stuck in there, what happens to the rabbit? He dies and rots, and it's gross, and you wind up needing to buy a new hat as well as a new rabbit. So the moral of this story is, boys and girls, to don't forget to pull the rabbit out of the hat. This is the rabbit. That is the hat. Step 1 of factoring a non-monic polynomial is to set poor little rabbit into the hat. And now we have the magic polynomial. It's the magic polynomial because, in fact, it does not So since whatever symbol is in that first position goes to whichever number is there. And now you have opposite signs. Okay. Okay, fantastic. Are we done? What have we forgotten to do? You have to pull that little rudent out of that polynomial. Now, which one of the two compartments contains a GCD of one radic? The 3x plus 6. And out comes one radic. Okay. I can go into more examples of this because sometimes the rabbit doesn't want to come out, and you have to break him in half and rip him out in pieces. It's actually a lot of fun. Yes. So back up to here. The alter. Mike. Before. And what do we get back? And now your limit becomes relatively simple. In that bottom drawer, and see if you can find a roll of clear packings of very, very big bottom. Awesome. Thank you. Leave it out. Yeah, actually, I drew a very similar picture. Pulled rabbit out of that. Rabbits have pink eyes. Absolutely. All right. Next. Ornithoids or something. Anyway, so we wind up getting the limit as x approaches -2 of 3x minus 1 of x minus 4 cancels x is not equal to -2, and we wind up getting plugging straight away. We get -6 minus 1 all over -2 minus 4, -7 all over -6, which is 7/6. And we're yes. Good. Okay. All right. Now, I thought we were going to have time during flex today because I seriously, honest to God, forgot that you guys had all that stuff going on. All right. Okay. All right. Okay. So let's talk about asymptotes. Okay, there are three kinds of asymptotes. There are vertical. I always misspell this word. I think I got it right the first time. Woo! First time for everything. All right. Asymptotes. There are vertical. There are horizontals. obliques. Okay? Vertical, and I mean, we know these before, we know what they look like. They could look like this. Or they could often, or sometimes they look like this. They don't have to be going in opposite directions, you know? They could go one and go the other. They can both be coming from the same direction. Horizontals. And oblique. I think they're fun. And like that. All right. Verticals occur when you have something in your denominator and you have a discontinuity in your denominator. When you remember all those places where we said x can't be 2, or x can't be 0, right? That indicates a vertical asymptote. Right? That tells you you have some sort of vertical asymptote silliness going on. Okay. Horizontals occur when you have something like that. Actually, I should be very careful right here. Where they are both equal to each other. Okay? Or, actually, they could be, the denominator could be bigger. And so let's change this. Make this n, where m is greater than or equal to n. So in a sense, if you were looking at a polynomial divided by a polynomial, my denominator is bigger. Okay? Meaning that it has a bigger exponent. Okay? So as this thing grows, my denominator is getting bigger faster than my numerator is. Okay? So you can think of this as bottom heavy or even. Okay, when I'm talking about my exponents. Does this make sense? Have we done this before? Yes. Yeah. And here, my numerator is this is top heavy. You guys remember how to do synthetic division? You guys remember how to do long division? Which one do you like best? Good. You're welcome to it. I do long division. You guys are welcome to do either one. I'm not a fan of synthetic division, but it's akin to witchcraft. Seriously, it makes me feel like, some sort of voodoo just happened on my paper and I don't know what happened. But long division looks good. I suspect. Well, but for your case, you have to do division. It requires division. All right. We have 10 minutes left. 12 minutes left. asymptotes for this function. Oh, no, you did not. Okay, we saw this function earlier today, right? When we were taking a limit, right? Remember? We were taking a limit of x as it goes to infinity. This is the one we played with earlier. All right. Well, the limit as it approaches infinity is -1, right? But let's take this thing and play with it a little bit further and find all of my asymptotes. So the first thing that we did was move around the denominator a little bit. And then we all right. At this point, we were down not equal to 1. Okay? So immediately we know that we have a vertical asymptote. Vertical asymptote at x equals 1. Right? Now, we have a horizontal asymptote as well, because my exponents in the numerator and denominator, well, no, they're equal. X squared and x squared, exponents. So if you think about it in this sense. Everyone's kind of in the sand. When you're digging a hole, the sand is trying to fill itself back in. It's dry sand. And there are three situations. One, you dig faster than the sand falls in. What happens to the hole? It gets bigger. Situation two, you dig at the same speed that the sand is falling in. What happens to the hole? It stays the same. In situation three, you dig slower. What happens? Well, it fills itself in, and every few minutes or so, you're lazy enough to scoop one more thing on. Next time you turn around, it fills itself back in. So these are our three situations. If it's top heavy, it blows up because my denominator does. If they're even, they cancel each other out. Because what happens is, if you think about this function right here, and I go towards infinity, right? Let's plug in forget about infinity for a second. Plug in a huge number, say 1,000. So now, if you were graphing this thing, and if you were graphing this function, and you plugged in 1,000 into your calculator, you would wind up with a really big number in your numerator. It would be 1,000 times 1,000, which is 1,000,000, minus 3,000, which is still really close to 1,000,000, plus 2, which didn't do anything realistically. And now down below, you plug in 1,000, you get 1 minus 1,000,000, right? So what happens is that all of this 3x and this 2 are really unimportant to me. So the only thing I really care about are my exponents. And in fact, I think this one's better. Because what's happening is you have 1,000,000 minus a whole little bits, and then you have 1,000,000 minus 1. And 1,000,000 minus 1 is still basically 1,000,000. And really what you have is you have 1,000,000 over 1,000,000, and they cancel out. Except for 1, -1. So as this thing goes off to infinity, as the limit, as x approaches infinity of this thing goes to -1. Now, if you here even, it would be fine. You would get the same basic thing. You plug in 1,000, or you plug in 1,000,000 or 1,000,000,000 or any huge number you can think of. 1,000,000 minus 2 divided by 1,000,000 plus 1 is still going to be 1, and then -1 is still in the game. Now vertical asymptote is what's left over. So I have here a vertical asymptote and a horizontal asymptote. So we get holes. Let's summarize this. That's better. Okay, factor everything in all the time. Now, sometimes people just give holes. Three. Counting. Now, sometimes if you plug in infinity at step 4, you might explode off to positive infinity or explode down to negative infinity. In that case, you have an oblique. And at that point, you're going to have to fool around with division. And at that point, you have to do synthetic division or long division, whichever you prefer. And you would then, whatever line gets produced from that. I don't know if we're going to have time for that, but maybe we can do one. So, for example, let me see if I can find a good one that we can do synthetic division for. This one. All right. Yep. All right. And by the way, if you ever thought that I was truly evil, reconsider that, at least today, because I'm giving you no homework over a 3-day week. This time. What? Oh, you're wrong. Okay, now take a look. Here, if I go off to infinity, I'm top heavy, right? I am top heavy. I have a problem here. Okay, so that means I have some sort of diagonal line that is my asymptote, some oblique angle, some oblique line to fool with. So if we do synthetic division or polynomial division, whatever you want to call it, okay. How many times does x go into x cubed?
3. Well, x squared.
How many times does x go into x cubed? Or a better question, what do I have to multiply x squared by in order to get x cubed?
X.
Thank you. So now we multiply it out.
How did you use your shortcut?
And at this point, gentlemen and ladies, I don't even have to go any further. I can stop right there. Because in order for me to go from x squared to negative 2x, I would have to multiply it by negative 2 over x, which is not a straight line. Really, all we're looking for is we're looking for a limit, sorry, a straight line this thing is going to behave on. And basically, if I go in here and say this is not the straight line that we're interested in, and in fact, we can probably keep going for a long time. We don't even need it. If I was able to get, sometimes you'll have like x plus 2, and that means you have a line intercept of 2. There you go. All right, ladies and gentlemen, enjoy a lot of 3-day weekends. Thank you for all of your help. This was great. And this episode of the Loco Show has been brought to you